Yes, okay. I'm AHMED SHEHATA, master degree student from Alexandria University, Egypt. My research is performance evaluation of a new liquid-to-air membrane energy exchanger, which is a energy exchanger utilized in a new air conditioning system that use liquid discant. I will go through a quick introduction, and then I will introduce a proposed module and system description, and we'll go fast along the mathematical model, and then we will show the results. First, for the introduction, the past researchers along the past 2 decades have been focused on liquid discant air conditioning systems. So what liquid discant air conditioning systems give us more than vapor compression or the traditional air conditioning systems? It saves up to 40% energy. Why this? Because they decouple the heat of latent absorption than the sensible heat. In this process, the vapor compression system, which is old or the traditional systems, use deep cooling under dew point temperature. This process uses the compressor of the heat pump and consume more energy. The liquid discant air conditioning systems are based on a natural phenomena. The natural phenomena is the absorption. If we get a cup of water and we drop salt in it, so it became a salt solution, the water vapor pressure difference between the solution and the air absorbs the moisture from the air, and the air is being dehumidified. This process or this natural phenomena is affected by 2 factors: the salt concentration, how much is concentrated, and the solution temperature. As long as the solution is more concentrated, as long as the solution temperature is low, the vapor pressure difference is bigger and more absorption can occur. Let's see how this is translated into system. In our system, we have a dehumidifier. The dehumidifier is the place where the fresh air meets the liquid discant solution. Fresh air meets the liquid discant and get out cold and dehumidified, because the liquid discant sprayed is cold in the evaporator before spraying and is concentrated, okay? But here, when the liquid discant is going to meet the fresh air along the dehumidifier, as long as he absorbs water, the concentration decreases. So the efficiency of the device decreases along the way. This is a case that we studied in this research. This dehumidifier is usually used by liquid-to-air membrane energy exchanger. The advantage of using liquid-to-air membrane energy exchanger is that this exchanger is not direct, it's indirect, as fresh air pass and liquid discant pass. Between them, there is a permeable membrane. The membrane allows the transfer of moisture, but don't allow the transfer of liquid streams to air. And this is important so that the air streams that is supplied to the room don't have these salt droplets that can damage the electric device. What we did here is that we introduced this coil, and this is the new name of our proposed module, embedded refrigerant coil. The embedded refrigerant coil is a coil of heat pump cycle. This coil could be used as evaporator and as a condenser. The coil is embedded inside the solution stream, so that if we go back, we have integrated this evaporator into the dehumidifier. This integration results in the new system that we talking about. The new module is used as the humidifier and the same time is used as the evaporator, so that during the journey of the fresh air along the dehumidifier, the solution will always be in a cool temperature, so that the driving force is increased and the overall efficiency increases. And then when it comes out a bit diluted, it goes through the regeneration stage. And in the regeneration stage, the solution dissolved out the extracted water so that it came cold again. The difference between two stages is that the liquid is here cold in the dehumidifier and the liquid is here hot by the condenser coil. So that the difference here, the driving force was from liquid from air to liquid descent, the water transfer from air to liquid descent. Now in this stage on the regeneration, it is reversed. The water skips from the liquid descent to the outside air. This unit is built or to be placed outside the conditioned space, and this unit is placed inside the conditioned space. Between them, there is a heat exchanger to exchange the heat and make more beneficial of energy. Let's discuss the mathematical model. The module we have proposed are governed by those governing equations, the continuity equation, force mass flow, conservation of momentum, conservation of energy, conservation of water vapor in airstream, and the conservation of water in salt solution. Please, if you have any question or anything is not clear while I'm talking, please feel free to stop me. Okay. In this paper, we will simulate the whole system, and we will see the performance of the whole system as a unit, so that we use these two equations to model the other components of the system. All the governing equations are used for the liquid-to-air membrane energy exchanger, but to couple the two membrane energy exchanger, we use the heat exchanger equation, which is the efficiency equation, and heat pump module by Carnot efficiency. Now the performance parameter, those equations will guide us to see the performance of the new equipment. Specific dehumidification power, it represents the amount of water absorbed to the total area of the device. Overall system coefficient of performance, which is a well-known factor that is used to analyze the performance of air conditioning. It is useful cooling capacity to the work total, and the energy efficiency ratio. It is newly introduced, which is the same as COP. But here, as we make beneficial of both evaporation heat and condensation heat, so that we add the QC to the QE above the work total. For the result in this study, we didn't make our research experimental due to the looking for the virus. So we used a numerical simulation study using COMSOL software, which is a CFD numerical study. And for sure, we have built a new numerical model for our device. So we need to first validate, is it validated to be used and to take its number or not. So we made the validation with past experimental result by Zhang from China, and his paper from 2018. In his paper, he made experimental and numerical model also. Our new numerical model results for the air temperature out and the humidity out results are more close to his experimental results more than his numerical model. As we see, for temperature, the results are below 6%, and for humidity are below 10% for all experimental steps. So it is validated and it could be used to our model. First, this is a design parameter. We have set a set of design parameters, initial parameters for all the system. And then we have set the operating parameter. There are two types of parameter. Operating parameter is a parameters that the operator of the system can use to change or to control the system. And there is an outside air condition. And for this study, we have taken typical hot and humid summer condition of Sharm el-Sheikh city in Egypt as per the annual dehumidification design condition of AHMED. Okay, and for regeneration air, it is room temperature. So we will take out the regeneration air from the room, the exhaust of the room, to regenerate the system. Okay, for these conditions, which is a design parameter or design conditions, the conditions where we designed this system at, these are the results. The results are very, very significant from 30-degree temperature Celsius and 19 gram water to kilogram air humidity. We reached 20-degree temperature and 6.5 gram to kilogram humidity. System specific dehumidification power is 130 gram per hour per meter square. The system cooling capacity is 41. And here is the most important, the COP is as high as 6.37, which is higher by 20% from traditional heat pump liquid DESICCANT system due to the efficiency of temperature used, the efficiency of the coil embedded inside the dehumidifier. Coupling them together have increased the efficiency of absorption. Now we will discuss, this is a design parameter, and this is a varying operating condition. If we will vary any of the operating condition, what is the results? For changing the solution flow rate, if we change the solution flow rate of the cycle, changing the solution flow rate from 0.5 to 2, 0.5 equal to the used mass flow rate here, is half flow rate of air. The flow rate of air used 1 kilogram per second. Okay, we will notice that increasing the flow rate increases the internal cycle of liquid DESICCANT temperatures inside the systems. Okay, and accordingly, the solution concentration increase and the humidity decrease. But here, the temperature increased from 20 to 24. So we have gains in specific dehumidification power, but we lose some cooling capacity, which is clear here. And these are the figures of the powers of the QE, the heat of evaporation, the heat of condensation, the work, the cooling capacity, and it reflects on, of course, on the system overall performance, system coefficient of performance, COP. The COP decreased, as we see in the red, but the specific dehumidification power increased. So we have a trick in the system. If we need more specific dehumidification power than the design point, we can gain it on expense of the power used. The second and final parameter is the evaporating coil temperature. Of course, we are use the heat pump so we can control the temperature. We can use the temperature to be controlled. And as we decrease the temperature of the coil from 16 to 8 degrees, system temperatures inside the cycle increase and the salt concentration, the dotted lines increased. The increase in concentration increases the absorption effect and the range of vapor pressure difference, so that more absorption take place, so that we reach by air humidity ratio to nearly 2 instead of 6, and temperature decreased as overall temperature decreased of the salt from 20 to 16. And finally, in this case, the specific dehumidification power also increased from 130 to above 150. And for sure, this all is on expense of the coefficient of performance, which deteriorates from nearly 6 to 3. Thank you, and for any clarifications, please feel free to ask.
Thank you, Ahmed, for your wonderful presentation.